Hello everyone, I'm Wang Boxuan, and my student ID is TCM2409005. And the topic of my presentation is the intermediate value theory. Here is the content. It mainly includes 4 parts. The first one is what does the intermediate value theorem say? Then the expression and specific examples of the theory. The third is the significance of the theory. Last part is the summary. Okay, the first one. What does the intermediate value theory say? First, let's define what the intermediate value theorem is. I'll briefly call it IVT below. This theory describes the behavior of a continuous function of a certain interval. Specifically, if you have a function f of x that is continuous on the closed interval from a to b, then if f of a and f of b are the values of the function at the endpoints of the interval, so for any value y between f of a and f of b, there exists at least one point c in the closed interval from a to b, such that f of c equal to y. In similar terms, if you walk along a continuous curve from point A to point B, you are guaranteed to pass through a point whose function value is some number between the values of the function at A and B, just as shown in the picture on the right. We randomly select 2 points on the curve with the horizontal coordinates A and B. Then we can definitely find a point C in the closed interval from A to B, such that the function value corresponding to C, so we just call it y, is greater than f of A and less than f of B. So the definition of the theory has 2 key points. The first one is the continuity. This is a core condition of the theory. The function must be continuous over the entire interval with no breaks. The second one is closed interval. We are talking about a closed interval, meaning the endpoints A and B are included in the interval. Okay, now is the part 2. The expressions and specific examples about this theory. Let's first take a look at the mathematical form of the IVT. Suppose that f of x is continuous on the closed interval from A to B, and f of A less than f of B. Then for any y belongs to the closed interval from f of A to f of B, there exists a point C belong to the closed interval from A to B, such that f of C equal to y. So in other words, if you choose the value y between f of A and f of B, the theorem guarantees that there will be a point C within the interval where the function value exactly equals to y. So to help you better understanding the intermediate value theory, let's use a real-life example. Imagine you are climbing a mountain from the peak A to peak B. Along the way, your height changes continuously. No matter which path you take, just as the image below, the straight path and the curved path. At some point, your height will exactly match any value between the peak A and peak B. So similarly, on the graph of a continuous function, as you move from left to right, the function value changes mostly from one number to another, covering all the numbers between the values at the endpoints. Okay, let's now look at a concrete example of how to apply the intermediate value theory. Finding a zero of a function. Consider the function f of x equal to x power 3 minus x minus 2, and we want to find a zero in the interval from 1 to 2. So the first process is to evaluate the function at the endpoints. Then we can calculate that the f of 1 equal to minus 2 and the f of 2 equals to 4. The next process, based on the intermediate value theory, since f of x is continuous on the interval from 1 to 2, and f1 equal to minus 2 and f2 equal to 4, with opposite signs, like one negative, one positive. So there must be a point C in the closed interval from 1 to 2 such that f of c equal to 0. Therefore, we know that there is at least one zero of the function in the closed interval from 1 to 2. This zero could be further solved using a numerical method such as the dissection method. So due to the time issues, I will not calculate it. Okay, the next part is part 3, significance of the every t. I will discuss its practical applications in this part. The first one is finding zeros of functions. The intermediate value theory is a fundamental tool in numerical computation, especially in finding zeros of equations. By applying this theory, we can ensure that there is a solution in a specific interval. What's more, analyzing the behavior of functions. This theory also helps us understand better how a function behaves on an interval. If a function is continuous, it will cover all the values between the values at the endpoints of the interval. This property is important in many fields like physics, engineering, and economics. Among them, the three major theorems belong to the calculus module, namely Rolle theorems, Lagrange theorems, and Cauchy's theorem, playing an important role in analyzing the properties of functions. So last but not least, the third one, guaranteeing the existence of solutions. In many mathematical problems, the intermediate value theory provides a guarantee that if a solution exists, it will be within a specific interval. No matter how we approach this solution, we can always find it within the interval. The intermediate value theory is also used in daily life, such as the interval speed measurement on the highway, which is the average speed calculated by distance and time. The theory ensures that the instantaneous speed is equal to the average value at least one moment. In addition, the theory is also very useful in medical drug preparation, mechanical design, and so on. Next, the last part, summary of the presentation. So, to summarize today's discussion, the intermediate value theory guarantees that a continuous function will cover all values between the function values at the endpoints of the interval. This theorem is not only important theoretically, but also has widespread applications in practice, such as finding the zeros of equations. As long as the function is continuous, and we know its values at the endpoints of an interval, we can apply the intermediate value theory to ensure the existence of certain values. The intermediate value theory gives us more confidence in mathematical analysis, as it provides a powerful tool to prove the existence of certain results. It will help us a lot in our daily study life in mathematics. So that's all of my presentation. Thank you for listening.